All right, we have a silly example here, just trying to, I assume the authors are just trying to get a little bit of a laugh. So, exploring a castle, Xena is spotted by a dragon who chases her down a hallway. She runs into a room and attempts to swing the heavy door shut. Okay, so I'm going to start sketching with this next step. The door is initially perpendicular to the wall. So I'm going to draw a view from above so I can draw the door. So here's a doorway, here's my door. The door is perpendicular to the wall initially, so she has to swing it through 90 degrees to get it to shut. Okay, the door itself has a height of 3.05 meters and a width of 1.15 meters. Its mass is 80 kilograms. We can ignore friction at the hinges. If Xena applies a force of 220 newtons at the edge of the door and perpendicular to it. So if I come back to my picture over here, she's applying this 220 Newton force perpendicular to the door. We want to know how much time it takes for her to close it. All right, so we're wanting to relate the force to motion, and specifically time, because that's what they're asking us about. Newton's second law is what will allow us to do that. The net torque on the door will equal I, the moment of inertia of the door, times its angular acceleration. All right, so torque in general, the torque due to any force is R times F perpendicular, or RF sine phi. The problem has already told us that she is pushing on the edge perpendicular to the door. We kind of have to assume that she continues pushing perpendicular to the door. Otherwise, we would need to know how this angle is changing as the door swings closed. So we'll assume she continues pushing perpendicular to the door, which is, I don't assume, a bad assumption. The torque itself will be R. R, remember, if we were to draw it in the picture, we would start R at the hinges and draw out to where the force is applied. So R is the width of the door. F is given, so we know that. I. Well, a door is a plane or slab. So if you look at the table, either in the book or on the test notes, you want to look for the plane or slab around its edge. When I look at our table, it says 1/3 MA squared. Now, this is a good place to notice what A represents. So look at the table from the book, and they have labeled the dimensions of the door, the width as A and the height as B. So what they mean here is 1/3 M. I'm going to just call it R, because we've already said R in terms of the torque is the width of the door. So I'm going to go ahead and just say I is 1/2 mr squared, where R is representing the width of the door. So alpha, let's see, we can cancel one of the R's. Alpha is our angular acceleration. We have the force, 220 newtons. We have the mass. We have the width of the door. The mass of the door, 80 kilograms. The width of the door, 1.15 meters. So we can calculate the angular acceleration of the door. So I'm getting 4.7826. This will be in radians per second because I have the width of the door in meters, the mass in kilograms, the force in newtons. So angular acceleration we have. Where to go from here? Well, we're looking for how much time it will take for the door to close, for her to close the door. Assuming she continues to apply the same force, we can then say that the torque is constant. I of the door is constant, so this angular acceleration is constant, which means the kinematic equations will apply. So let's see what we have. I'm going to write them all out, just here on the left. And actually, I'm only going to write the first two because we want time. The third one doesn't have time in it, so I'm not going to bother to write that one. In terms of what we know, we now have alpha. We can totally assume omega initial is at rest. I don't believe the door was already moving before she got there. The other thing we know is that the door needs to swing through 90 degrees in order to close it. So that is essentially an angular displacement, a delta theta. So theta final minus theta initial. Since I know an angle, I'm going to take this second equation. If I take theta initial to the left side, I have my delta theta. Since the door was at rest, this delta theta will equal 1/2 alpha t squared. So I actually have enough information to solve this for time. Now I cannot plug in 90 degrees, because remember, angular acceleration, we have the radians per second squared. The safest bet is to always get anything related to angles in terms of radians. 90 degrees. You may know right off the bat what it is, but we know there's 2 pi radians in 360 degrees. That goes in there 4 times, so we get pi halves radians. That's what I need to put in here for my angle, my delta theta. Now to finish my calculations, let's see, where's my pi button on this calculator? There we go. I'm getting 0.81 seconds. Is the time it would take to close the door. So relating a force to motion typically requires Newton's second law. And then because the acceleration is constant, we can use the kinematic equations as well. Okay, friends, I just found a mistake. I apologize. Anyone else see what I did? my mistake went off plugging in over here. I put it in 1/2 instead of 1/3. So this 2 should be a 3. The r's, one of the r still cancels. So my angular acceleration, let me fix that. Oh, that's not it either. Okay, 20. Get your decimal in there. Let's see if this. So the time with the corrected angular acceleration would be 0.66 seconds. That's pretty fast. Just over half a second to get that door closed. All right. I make mistakes just like the rest of us, everyone else. Sorry about that.